All right, those of you at home, welcome to Stoichiometry, but first, pause the video, copy this down. All right, y'all. What we're going to do is take the next logical step that exists after studying reactions, right? You're equipped with a bunch of skills now. You know how to translate reactions, turn English into actual symbols. You can predict products. I can give you almost any two reactants, and you can tell me that if you mix them together, what'll form, which is really cool. You can also tell me during double replacement what will stay solid and what will dissolve into solution. Of course, you can balance and track charge changes for single replacement reactions, a bunch of cool stuff. But here's the thing. All those skills is of little use unless you can control the quantities within reactions. It's one thing to be able to say, okay, well, if I mix these things together, it's going to make this stuff. But it's critically more important to be able to control the amount of the stuff you make. For example, one of the most common places that reactions are commonly run is a pharmacy, all right, where they make drugs, right? They make things like painkillers to hook you up if you have a headache. So when they're doing that, when the pharmacist is making a painkiller, well, that's the product. They want a painkiller. They know how to make it, right? That's why they have that job. They understand the reactants that they have to mix together to make that painkiller. But if they don't put enough of the reactants in and the painkiller is too weak, then it won't do anything. You can take the painkiller, headache's going to stay there. But on the flip side, if they use too much reactant when creating it, well, you'll never have a headache again. It'll be too strong and kill you. So it's got to be perfect, right? There is a perfect amount in that pill that they need to create. And the only way for them to know that is to know, okay, well, how much of each reactant has to react together to make the perfect amount of product. This idea is stoichiometry. It's simply taking the reactions that you've already studied and learning the quantities associated with them. This much of this makes this much of this. Now, for us to figure this stuff out, it is very mathematical, but it's also just a bunch of dimensional analysis. So if you're pretty good at my grids, then you're going to have no trouble with the stoichiometry, even though these problems are longer than problems that we've done in the past. I've also handed you out a sheet. All right. If you're at home and you don't have this sheet, you need to get the sheet. I mean, I suppose you could pause the video and get that information right there down. It's the most important part. But I have these in the classroom. Okay. Now let's talk about the sheet. Look at it. Look at it. There's a side that has less print and more of my writing, and a side that has more print and less of my writing. I want you to look at the side that's got more of my writing. It's got a tiny chunk of print up top and more of my writing at the bottom. Now, both sides of this sheet are the exact same thing. I mean, they have the same point, but written in different ways. I pretty much just cheat off the side. I teach off the side that I'm showing you right now. But if you read the other side, you'll see it breaks down the steps a little bit more than I do. And maybe you like it. I don't know. But this is yours as a crutch for now to use. Before we start, I do want to point out a vocab word. On the opening slide, you wrote that theoretical yield is going to be the answer to a stoichiometry problem. What we're going to do is, while we're figuring out, okay, if I start with this much reactant, how much product we're going to produce, and we finally get an answer, that answer is called a theoretical yield. That's an important vocab word, so just all of our answers today will have that label. There's another important sentence there about moles over moles. We'll do that when we get to it, but let's take a look at the conversion factors here at the bottom. You recognize them, yeah? You recognize the red? I'm going to give you those on the test. That red information will be there. I have it written again here. You recognize all of them except which one, though? Which one's new? The liters, yeah, the volume is new, but it's just another number, y'all. Liters is the amount of space something takes up. That's all it is. It only applies at STP, but you don't have to worry about that yet. While I am going to give you all of the red data, you will not have any part of this sheet on the exam. So the exam's really far away, but I just want to make that clear right up front. So with that said, all right. Go ahead and write down that reaction. You don't have to write down the question. I'll write it down for you. I underlined the coefficients so you can see them clearly. So it says that 4 nitrogen trihydrides react with 5 oxygens to produce 4 nitrogen monoxides and 6 waters. Yeah, you could do that. But we're not studying the reaction. Look what else it says. You didn't write it yet, but here's what I do want you to write. It says if you have 150 grams of heme, how many moles of heme will form? All right, so remember, the moles is our counting units. This number here is the moles. So when balanced, if everything's perfect, you get 4 moles. But if I sent you to the back and I gave you excess heme, do you see how it says that? Do you see how it says excess of heme? That means one of the reactants you have an infinite amount of. All right, we're not going to let him affect anything. But we only have 150 grams of heme, so the oxygen is going to be the reactant that could possibly stop the reaction. How many moles of heme will form? All right. Well, let's figure out how to make this painkiller then. I want you to look at that cheat sheet, and you'll notice at the top there's 3 steps. We're going to read through those 3 steps, and it's going to tell us exactly how to solve this problem. Step 1. It says the units associated with the given value must be in moles. It says the given information must be in moles. Is the given information in moles? No, it's in grams. So if you read the question, it says if it is in moles, awesome, go do the next step. But if it's not, then switch it to moles. But you've done this for me a lot of times. So let's get this set up. Here we go. So it gave me 150 grams of oxygen. But step 1 says it can't start in grams. The oxygen must start in moles. So this will be my step 1 conversion. You must start with moles. Now, what should I automatically put in this diagonal square? Yeah, you just take this and go there. For some reason, that's the point I still lose some of you in, and I just don't know how else to say it. All right, not the number, just the unit and the compound. Grams of O2. All right. Now, we know from the past that these numbers come from the conversion factors, which are located right over here, all right, or you wrote them on the opening slide. So what number goes with moles? 1. And what number goes with grams? The periodic table. All right, so it's the periodic table of 2 oxygens. What's that total mass? Yeah, it's 16 twice, right? Everybody okay with the 32? Sweet, run it. Multiply across the top, divide by the bottom. 150 times 1 divided by 32. And see if you like my purple number there. You don't, you follow sig figs. Follow your sig figs all the time. Now, if you're ever wondering about the units, you're like, well, how'd you know it's moles of O2? Right? It's always the top right square. All right, because mathematically what's happening is these two are canceling out because they're the same on the top and bottom. But even if you don't want to go all fraction on yourself, all right, whatever units are in the top right square are the units of your current answer. Hey, we did step 1. That wasn't so bad. Look at step 2. Step 2 says, convert the moles of what you're given. All right, now we were given oxygen, and now we have moles of oxygen. It says convert those moles to moles, but of the unknown. Step 2 is a moles to moles conversion. We are taking moles of what they gave you and turning it into moles of what they're asking for. So let's set that up. All right, it's just another one of these guys. Here we go. So I'm going to take that 4.7 moles of O2 and following step 2, turn it into moles of what it's asking for. What's it asking for? NO. Right, look here. Remember, it's asking about the nitrogen monoxide. Drag your diagonal. Now, something different happens here, and you wrote about it on the opening slide. If you look back to the opening slide, it says something about if moles of something is over moles of something different. Or if you look at step 2, because that's what we're on right now is step 2, it says for the mole-to-mole conversion, you're going to use the coefficients. It's underlined, all right? So whenever moles is over moles, you don't use the conversion factors. That's only if something is over something different. If moles is over moles, instead, you use the balanced coefficients from the reaction. So watch how easy this is, though. For NO, it's 4. And for oxygen, it's 5. Multiply across the top, divide by the bottom. What about 3.8? How does that make you feel? All right, well, now we have moles of NO. Now, there's another step left, right? There's a step 3. But what does it say? It says now you have moles of what it was asking for, but then it says if it wants moles, you're done. Does it want moles? Yes. So here's a little nutshell thing that you don't really have to, this isn't really a part of stoichiometry, but anytime moles is in the problem, if they give you moles or they ask for moles, that is good news for you. Because if they give you moles, you get to skip step 1 because you wouldn't have had to go to moles. And if they ask for moles, you get to skip step 3 because you don't have to turn this number into something different. So while you don't have to really understand that if you don't want to, I'm just letting you know that when you look at a new problem and you're like, oh my God, moles is in there a bunch of times, that means it's a shorter problem, which is good news for you. Anyway, this is our theoretical yield because we now have the exact thing that they were asking us to find. And we don't have to do step 3 because it asked for moles. Let's do another. Write down the reaction only, please. I will write it down for you, computer. You don't have to underline the coefficients. I do it for contrast here, but whatever. You can do it. Helps your focus for the mole over mole part. All right, now let's take a look at the actual question. All right, it says, if you have 290 grams, 290 grams of that guy, how many liters of him will form? Now it gives us excess of him, which means we have as much oxygen as we can do anything with. That doesn't matter today, it'll matter on Tuesday. That's a different thing. So cool, there we are. Hey, do y'all see any good news or just bad news in this problem? It's terrible news, right? And what I mean by that is moles isn't given and moles isn't asked for, which means we have to do the longest type of problem, which is really good for teaching them. So look at step 1. Reading off your cheat sheet, step 1 says, make sure you have moles. You've got to start with moles. And look what we're starting with. It's starting us with grams. So instead of starting with grams of aluminum, step 1 says we can only figure out the product if we start with moles of aluminum. Notice how the substance stays the same. All right, we're going from grams of the given to moles of the given. We haven't changed anything yet. What should go there? What should go there? What should go there? Automatic, right? So ridiculously stupid easy. Drag the diagonal. All right, so look, moles is over grams. That's the normal one, right? The only time it's weird is if moles is over moles. So let's go grab it. For moles, I grab 1. For grams, I grab periodic table. Just go look up aluminum. It's just Al1, right? You get 26.98. Make sure you know where that number comes from. Beat me to an answer. Watch your sig figs. Be good at sig figs. Woo! We did step 1. All right, let's just read then. Step 2. Step 2 says go from moles of given to moles of unknown. This is the moles to moles step. All right, it's the only step that you never skip, right? Sometimes you skip step 1, sometimes you skip step 3, sometimes you skip both. But you never skip step 2. All right, you've always got to go moles of known to moles of unknown. So now we have moles of the given. So let's take the 10.7 moles of aluminum. And we can now cross the reaction and go to a brand new substance, moles of known to moles of what it's asking for. All right, and look, it's asking for aluminum oxide. Drag the diagonal. Hey, look at this. Moles is over moles. Where are these numbers going to come from? The coefficients. This is the only time that we don't go to the conversion factors. Go to the coefficients. And now you can see that if you're still really bad at balancing and I give you an unbalanced reaction, stoichiometry is really hard because you need those coefficients. Anyway, aluminum oxides is 2 and aluminums is 4. See if you're okay with my green value at the end there. In the previous question, we stopped right here. In the previous question, it said, how many moles? Do we get to stop this time? No, because if you read step 3, it says, yeah, don't do step 3 if it asks for moles. But this problem is asking for liters. So step 3 says, well, but if it asks for something else, then just change it to that thing, right? It's not hard. It's just another step. So let's take the 5.35 moles of aluminum oxide. And what unit should we convert to? Yeah, just to whatever it says. Let's go to liters of the aluminum oxide. Drag the diagonal. It's not moles over moles, so use the conversion factors, all right? What's the conversion factor for liters? It's your new one. Yay, remember, I'm going to give you that number, so you're good. All right, and the conversion factor for moles is 1. And now you are a click away from a theoretical yield. Watch your sig figs. Anybody want to share their answer? Oh, you're in my biggest class. Yeah. Perfect. You're absolutely right. What's true about the 120 though? It should have a decimal. Right? Your answer is supposed to have 3 sig figs. And there it is, theoretical yield, final answer, and this is the hardest kind of problem. If right now you're feeling like maybe you're a little shaky because it's so new, but if you kind of get it, then you're in great shape. This is itching to death. All right, let's do one more, and let's draw a bunch of cards because that'll make you excited about my class. Copy down our final reaction of the day. All right, let's take a look at what kind of info it gives this time. All right, let's see. It says that it's going to give us 0.68 moles. It's going to give us 0.68 moles of him, and it wants to know about atoms of him. Do you agree? All right. Aspen's in play. Here we go. Let's go talk to some people, make you famous on my computer. Let's go over to cluster 6 and talk to seed 1. Hey, 6-1. In terms of step 1, do you have good news or do you have bad news in this problem? What? It is good news, right? Because look, this is the first time that it gave us moles. And if you look at step 1, I mean, it flat out says, if they give you moles, don't do step 1. Because step 1 just says, make sure you have moles. If you don't, get moles. And hooray, we've got moles of hydrogen. So we don't have to do step 1. We can go straight to step 2, where you go from moles of what you're starting with to moles of what you want. So let's get that set up. All right, so we've already got our 0.68 moles of hydrogen. And step 2 says, turn that into moles of the requested substance. And if you look closely, it's asking about gold. All right, let's go over to cluster 4 and talk to seat 5. Hey, 4-5, what should I put down there right now? Moles of H2. You did the diagonal drag, perfect. All right. Let's go over to cluster 4 again and talk to seat 5 again. That seems very cruel. I'm sorry. Can you give me these values considering those 2 units? Remember, the trick here is that it's moles over moles. So these numbers come from... All right, so what is it? So what's the coefficient of the gold? And hydrogen? Perfect. Everybody good with that? All right. What? See if you agree with the black value on the board. So we skipped step 1 because we already had moles. We did step 2. Am I still recording is the question. Yes, we're still recording. Okay, I don't need that. We skipped step 2. I'm sorry, stupid. My screen, for those of y'all that can't see at home, my screen went off and threw me for a loop. All right, we skipped step 1 because we already had moles. We did step 2. We went from moles to moles. Step 3 says, go from moles to something else you need. Do we need to do that step? Yeah, because it doesn't want moles. It wants atoms. So let's get that going then. Let's take the 0.45 moles of gold now, and we'll convert that to what it wants. Atoms of gold. Drag your diagonal. Go over to cluster 1 and talk to seat 3. Hey, 1-3, can you tell me what number to put in that square? So use the units. It's not moles over moles. So let this unit help you. All right, right, now it says particles on my board, but if you look at your opening slide, what does Avogadro's number say? Atoms and molecules. Atoms, molecules, particles, all the same thing. All right, so yeah, it's Avogadro is what you need here. And then for moles, of course, it's 1. And we will draw one more card for an answer. If you're sitting there and you don't remember how to get the scientific E23, talk to a elbow partner. They'll hook you up. All right, let's go get an answer over in cluster 5. We haven't got to talk to y'all today. Cluster 5, seat 5. Instead, it's Aspen. Hey, Aspen, do you have an answer to share? Perfect. 2.7 E23 atoms of gold. You're actually it doesn't go there; it goes to 1, but the class is over. So. Aspen says hi, people at home. Hey, real quick, I know you want to pack your stuff, but listen real quick. Tomorrow, we're going to practice more together, so you don't have to go home and canvas yourself out. Hang on. I want to tell you now, though, on Canvas, there's a Stoic 1 and a Stoic 2. They're both for grades, but you have unlimited attempts on Stoic 1. So you can use it to make sure you are a pro at this. Then Stoic 2 is the exact same type of problems, but it's your normal 2 attempts. More tomorrow coming.